Hello and welcome to Module 5, Network Protocols. Okay, so remember, I'm going to ask you to take some notes by taking screenshots or typing the notes and put them in Microsoft Word and submit them as evidence that you have viewed the lecture. Okay, so let's go over Network Protocol. This is really a review of the first course of your CCNA. Okay, so we will cover 3 sections. We will talk about network communication process, communication protocols, and how data is encapsulated before it exits onto the media or decapsulated when it is acquired from the media. So when we talk about networks come in many different sizes. They're small. You can have 2 computers that are directly connected to each other, to a very complex networks like the internet, which is, millions of LANs interconnected together through the public internet routers that interconnects them together. When you have a peer-to-peer network, such as this, so a peer-to-peer network is when you have few computers or devices that are interconnected to each other, and they are set up to to share files or things like that. There's not one computer that is in control of anyone other's computer. So in a peer-to-peer you're just able to see each other for emails, for sharing files, for printing, for example. Many home networks are designed in a peer-to-peer network. So please write this final, that last bullet point on the bottom. You may also have a small office, home office, such as, this cubicle. This is where you have, you do a lot of your work, a lot of cubicles on one floor. When they're all interconnected together, they may share maybe 2 or 3 printers that are pooling together. So if if one printer is busy, the other printer will pick up immediately, and things like that. They are all typically connected to one switch, and then they are also connected to a router that will take them out to the internet. Then you have these medium to large networks. We have companies, and they may have within a city, they have many buildings that interconnect to each other. Okay, so these are used by corporations or schools. So you may have a university that has many different buildings, and even within the city itself, they may need to connect to. Routers may be used to route between these networks. So there has to be some sort of redundancy in there too as well, to make sure that all of these networks are interconnected to each other. Or you may have a big enterprise network that, or that has branches all over the world, and they may use the internet to interconnect with each other. But remember, if you need to use the internet to connect from one site to another site, you have to use a VPN to make sure that your data is secured. We'll talk about that as we move later on. In a typical enterprise network, it is a small network, or so you may have what we call a client-server network, where you have a client. A client is a computer, such as Windows or a Mac machine, that needs to connect to another computer, a server. So what makes that computer a server is the one that has a special software that enables it to provide services for the clients, such as that Mac machine or another Windows-based computer. So what kind of services? You may authenticate that person, gives them some rights and privileges, permit them to access specific resources, give them IP addresses, given some access to certain applications and resources. You'll know exactly when they came in, when they logged in, when they logged out, and so on. So please write down the 2 bullet points, the middle 2 bullet points in the middle. all devices that connect to a server and need to be authenticated and authorized and have access to certain resources, the server, they need to access that server. That's called a client. Those are called clients, such as a workstation. Even a printer can be controlled in a domain area by a server. So a server is the guy that controls all the devices, all the clients in a domain, in an area. And typically we have on that server a Windows Server 2019, let's say, and we activate the Active Directory in that domain so it can control all of these users that are in there. So here is a typical client server. Here's the file server, and all of these can be considered, these three guys right here can be considered clients. So if they need files, I'll go to the file server. If they need to access web pages, they may go here. If they need to access their email, the email will do that service for them. So that's why we call it. Now, all these three devices, the web server, the file server, and the email server, could be one device. Like the Windows Server 2019 enables you to have all of these different services on one computer. Windows Server 2019 enables you to do that. All right, so typical sessions, you may be at school. All universities, colleges, high schools, typically they have their own client server. They have their own server they want their students to have access to. Specific resources, specific applications they don't want them to access. For example, the internet while they're on campus or using their own devices and things like that. You have more control of what they can and cannot do. And you don't have to be wired all the time. So students may bring their own devices, such as their laptops or even their phones or tablets, and connect to the school's network. The school itself may be connected to the internet as well. So they have their own speed that allows them to connect to the internet. You may be connected to a network while you're playing a game. So you connect to someone else in a different part of the country or a different part of the world, and you can play a game remotely. So you and that person have your own servers. You service them, they service you, and you connect to them most likely through a VPN. And you can, if you have good enough fast connection, you'll be connected. That's kind of peer-to-peer network when you're playing a game. But you are both considered to be servers. Medical consultation. Let's say you have a doctor, and that doctor wants to have access to his patient's records. He wants fast connection. So there's a server that has all the patient's records, all the information that he needed, and he can access it very, very quickly. This is very, very important. Almost all hospitals have IT department that is 24/7 to make sure that the doctors and the hospitals are running 100% and there is no delay whatsoever in terms of connecting and trying to get their resources. A person that works in a hospital, and every month he has a weekend, he's on call 24/7 on the weekend. They do pay him for that, but he has to be around to make sure that in case something was wrong, he make sure that the servers and the doctors and the computers are up and running 24/7. And a lot of the work that you, as an IT specialist, a lot of the work needs to be done off hours because you don't want to make any changes or upgrades or maintenance, between 9 to 5, because that's when everybody's working. A lot of the upgrades happen after hours. So just keep that in mind. All right, so if you want to know tracing the path, meaning finding out exactly where your data. So let's say when you send out your data goes and takes multiple paths to get to the destination. There are tier 1, tier 2 connections over the internet. But in general, when you're sending your data to your service provider, whoever your service provider is, you pay for the connection between you and that service provider. So let's say you're paying for a gigabit Ethernet. You're paying for that connection between you and your service provider. Your service provider then takes your data and throws you onto the internet. It may go through tier 1 or tier 2, but these routers over the internet are super fast. No one. This is the super highway. And they are free, in general, and they are the data as it travels, they are unregulated. But you don't know which path, you have no control which path your data is going to take to get to the destination. Once you're on the internet, you're pretty much on your own. So that's why it's probably a good idea if you need to connect to someone else on the other side of the internet, that you create a VPN. You encrypt your data, and that encrypted data goes through a tunnel. It's re-encapsulated into another packet. And as it traverses the internet, if anybody's eavesdropping, it won't be able to decipher what the data is. Only you and the destination will be able to figure out what the data is, because you have the key to unlock the VPN and be able to read the data. Okay. Communication protocols. To be able to communicate, you have to follow certain standards. Protocol is mainly a standard that you have to follow. So there are standards or protocols on how the message is going to be encoded. What does a 1 and a 0 mean when you are transmitting it? The message format, how do you encapsulate the data? That's like if you are encapsulating a letter, an envelope, there is a standard on where you put in the source address and the destination address. Same idea when you are encapsulating data, when you are sending data out of your computer. It goes through an encapsulation process, and the labels that are placed on each of those. How big the message size. There's a limit to how much data you can send. This is like if you're going to the post office and you bought a 100-pound box and you want to send it through the mail. But the post office tells you that, the limit is 20 pounds. So you have to go back and put it in smaller boxes, maybe 5 smaller boxes, and relabel each one of them, because there's a limit to how much data you can send. The timing, you need to know exactly when the receiver, or let know the receiver when they going to be receiving the data and how fast, right? And the different types of message delivery. Do you want to control and make sure that the data gets there? Or that's, it could slow things down. Or do you want to speed things up a little bit, right? This is like going to the post office and say you want a certified mail to make sure that the guy receives it, and you get a message that the guy has received it and you can track it. You pay a little bit extra for that. Or you just want to send regular mail, which really doesn't cost you anything. But anyway, as long as you follow those different types of protocols, so please write these down. Protocols are standards that will set limit on what type of message you are encoding, message format and encapsulation, the message size, message timing, and the message delivery options. There are protocols for all of them. Okay, now on the internet, so you may have HTTP. So if you're trying to access, for example, a web page, yahoo.com, so your browser will use the hypertext transfer protocol to go and to the yahoo.com server somewhere and look for a file called index.html and transfer it to your browser. Your browser will take that file, look at it, look at all the HTML codes that are in that file, and then display it for you. It uses the TCP, when you get transmission control protocol, to access that file. It's going to grab all the files and put them together. We'll talk about TCP and IP later on. But, it uses to make sure that the data gets to you. And if it was corrupted, it will go get another one, another piece. All right, so the message structure, how does a message look like? So you have an IP packet, you have the data, and then you attach to it labels. This will make it a packet, right? And routers will only read the IP addresses on the packet before they send it out. You may think of routers are like post offices. And when you send an envelope to the post office, they look at the zip code to determine which is the next post office to send it to. So routers will look at the IP address, the destination IP address that is stamped on the packet, to determine should I send it here or here. So it's probably quicker to send it to this router according to the IP address. So the whole world is broken up into areas, and each area is given an IP address. IP address identifies the location that you are in. They are similar to zip codes. Path sharing. So the routers, these paths, data being sent, some data may go on this path, somebody else's data may go on the same path, right? And the way you get to your destination, depending on the labels that are stamped on the package, okay? And these routers talk to each other, and they know where all the networks that are connected to them. So they are also responsible if a path goes down, they talk to each other not to use that path, like here. Information sharing, like I said earlier, routing protocols share information to each other about which networks are connected, which are not. That's why when you ping sometimes or trace a route, information are sent back to you telling you that, the network that you're trying to reach is unreachable. Your packet has died, timed out. The ICMP protocol is the one that does the session management. Keeps track of all the links to make sure they are up and running. And if there is any problems, it relays that information back to everyone that's connected to let them that this link is broken and no one needs to use it. If your packet loses its TTL number, it will send an echo reply to the originator to let them know that the packet has not, timed out. Their time to live number has reached 0 without the packet actually getting to the final destination. If that ever happens, you need to use traceroute to trace and find out exactly where that problem occurred. Okay, so in the old days, in the early 1970s, Department of Defense has the TCP/IP protocol. Sometimes we call this the excuse me, the 4-layered DoD model, the Department of Defense model. And you need to remember that. So please take a picture of this. It's very important because that's pretty much how the internet works. You have the application layer, transport layer, the internet layer, and the network access layer. So for example, if you ever need to design a simple mail transfer protocol server, a server that accepts emails. So you use the application layer protocols to develop your SMTP server. So everybody that wants to send emails will be able, and they all use the SMTP standard. Your server will be able to accept their emails. So if all the emails will use TCP, connection or TCP is a connection oriented. So if you want to send out an email and you want to use TCP, and anyway, by the way, you have to use TCP. You want to make sure the data gets to the destination. Connection oriented means TCP will go out and make a connection with the destination you're trying to reach before you send any data. This is like calling your friend before you go to their house to make sure he's there. You connect. You don't want to go there, drive 50 miles, he's not there. That's why connection oriented. If you're UDP, you probably will do that. That's connectionless. All right. Then you need to use either an IP address like IPv4 and IPv6 to identify the source, where are you located, the source and the destination. And then you pass your data to another device that is directly connected to you using the access layer, using the MAC address. So MAC addresses are used to communicate with devices directly to each other in a LAN. IP addresses identifies the location, the area, the network that you are in, and the port number, which all of these applications have port numbers, are unique port numbers that they use. For example, SMTP has port 25, HTTP has 48. I'm sorry, 80. HTTPS has 443. So each port number identifies what type of application that you're trying to reach. So, as a review, port number identifies what type of application you're using. An IP address identifies the location, the area that you are in. And the MAC address identifies your physical address, who you are in that LAN, in that location. And that's what you use to communicate with other devices in your LAN. All right. To be able to get an IP, here's a couple of things you need to remember. You get your source IP address, please write these down. You get your source IP address from a DHCP server. You get your destination IP address from a DNS server. Okay? You need those IP addresses to be able to communicate. People need to know where you are from, which area you are from, and which area, the computer or the device, the server that you're trying to reach at destination. So that's why you type a name. You type www.microsoft.com. So your computer will go immediately to a DNS server trying to look up the name Microsoft.com and will translate that name to an IP address, to a destination IP address. Gives it to you. You stamp it on your packet. You got your IP address from your DHCP server, and then you send your data out. Well, actually, you give it to your NIC, and your NIC will encapsulate that data into a frame and then send it to the default gateway. All right, so you may take a picture of this, but remember, you need to know that DNS is the one that assigns the destination IP address, and the DHCP is the one that assigns the source IP address. Here are different protocols also that operate at the application layer. You may have an SMTP server. SMTP server is where you send the data to, your emails. The POP server and the IMAP servers are the ones where you retrieve your emails from. FTP servers is where you can upload and download files by just clicking on, by just clicking on a link. The SFTP, the secure FTP, will allow to make sure that the files that are being uploaded and downloaded from the server is secure. They use the SSH. TFTP is for trivial file transfer. This is for you directly connected to a switch or a router or another device where you don't need any authentication or any encryptions. So very, very quickly you can upload and download files from a device that doesn't need to be authenticated or the data needs to be encrypted at all. Then you have the HTTP, the hypertext transfer. Of course, you want to use HTTPS. HTTP is how do you actually go and get a web page from a web server transferred, but it gets transferred in unencrypted. All the data is unencrypted, and that's hardly anybody does that anymore. Everybody uses HTTP. So as the data traverses the network or the internet, the data is encrypted to make sure that no one will be able to eavesdrop and read your data. There are two ways that you can transfer the data. So at the transport layer. So all of these different protocols that we talked about, they all need to either use TCP or UDP. For example, TFTP will use UDP. SMTP or HTTP, they use TCP. As a rule of thumb, please write these down, by the way, the responsibility of the transport layer. They got these two protocols. So in general, if your data is leaving your LAN, you're going to use TCP, the transmission control protocol, to make sure that your data gets to the destination. If you are trying to communicate within the LAN, you don't have to go outside, and you need speed and quickness, you may use UDP. Okay? TCP is connection oriented. It's going to make sure make a phone call to your friend that you are there before you send and receive any data. It's reliable. It's going to make sure all the data gets there. And if any of the data that is received is corrupted, the destination will ask the source to resend the data. And it controls the transmission. The destination always tells the sender to either slow down or speed up the amount of data that's being transmitted. Now, TCP is slow, but again, it's reliable and it's going to make sure all the data gets there successfully. UDP, on the other hand, is quick, but it's unreliable. There's no technique. If the data gets corrupted, that's too bad. But the only advantage is most likely you're sending and receiving data on a two directly connected device. So there is not a lot of corruptions. Okay, at layer 3, this is where IPv4 and IPv6 takes over. This is where you need to know the IP addresses. And remember, the IP addresses identifies the area that you are in. Okay, so we also talked about routing protocols. The most widely used one now on an enterprise network, not on the internet, for private network, is OSPF. And what these routing protocols do is routers use them to talk to each other to update the routing table. A routing table consists of networks and what path they need to take to send you data. This is like the post office. When you send them a package, they look at the destination zip code. So the router will look at the packet destination IP address and look up a chart to find out where this destination needs to go to. And they need to send it to another router. So the post office, for example, sends data. If your data is going from Florida to New York, it will send your package north because the zip code of New York is north, not west. So that's why when you're tracking it, it takes hops going north from Florida to Georgia to South Carolina and so on. Routers do the same thing. They look at the destination IP address and figure out where is this IP address located in the world, and will send it to the next closest router. How does the router know it needs to send it? Where did he get that information about where that destination IP address is located? They use the Open Short Path First routing protocol. Routers talk to each other to update them, to tell them where all the networks are located. Excuse me. All right, when you are in a LAN, anytime you want to send data, you need to get the device that you need to send the data to, you need to get his MAC address, his physical address. So the packet that you are sending gets encapsulated in a frame. The frame is created by your network interface card. If it's wireless, most likely it's 802.11. If it's wired, most likely it's the 802.3 Ethernet. But to get the IP address, to get the MAC address of the device that you need to send your data to in a LAN, you have to send out an address resolution protocol, an ARP request. So an ARP request, write this down, all these bullet points at the network address. The ARP request will request the MAC address of a known IP. The MAC, sometimes we call it the MAC address, is the hardware address, the physical address, or the MAC address, right? I need your physical name so I can stamp it on the frame, send you the packet that is encapsulated inside the frame. All right, so like I said earlier, this is an analogy to an email. So all that encapsulated, the letter inside is your, let's say, a web page. This is where the source IP address gets stamped, the destination IP address. There's a protocol on where you put these. You can't put the zip code anywhere you want. So this is where your IP address, destination IP address, source IP address. The address on Main Street, that's the MAC address. This is the destination, this is the source. The name of the person that lives inside that house, because there's Mary, John, Joe. This is like the protocol. What type of data that's in there? Who is the letters for? So the source support number is the name of the person. MAC address is the name of the building. The IP address is the zip code. Perfect analogy. And the router is the post office. The switch is the mailman, because he knows everybody in the land. Here's a typical packet and the labels that are stamped in it. Okay? So these are just the labels. Look at the IP address, the destination IP address. This is, I think, IPv6 labels. IPv4 has a lot more labels. So routers will lead destination IP address label to figure out where this needs to be sent to. Okay, like I said earlier, the message size is limited. In fact, the Ethernet frame cannot be larger than 1,518 bytes. If it's larger than that, Ethernet NICs, network interface cards, will drop them. So there's a limit, and you will not be allowed to create what we call jumbo frames. All right, so message timing, you need to make sure that the guy knows that you're calling. So you contact them, you get connection oriented, you let them know how fast you're going to be sending the data and what type of access method. You know, if I'm talking, you don't talk. So that's the access method. And when do you disconnect, for example? All right, so next is we need to talk about the unicast, multicast, and broadcast. Please write the definitions of each. They are maybe self-explanatory, but you need to know what they are. So a unicast is when you are sending a frame to only one device. So the destination MAC address on the frame is only for that one device. And then when the switch reads that MAC address, he knows where that destination is and sends it only to that port. That's a unicast. Multicast, which is class D addresses for IPv4, you read that address and you send it to everybody that has joined the IGMP, the Internet Group Messaging Protocol. So in addition to your IP address, you may have another IP address because you're part of a group. So when the switch reads a destination IP address is to a group, let's say class D 224 whatever, he will send it to all these people that have joined the group. So multicast is when you're sending data to a group of people in a LAN, not everybody. If you want to do everybody, that's what a broadcast is. So when the switch reads a frame that has all ones in it, the destination IP address, he sends it to everybody. It's flooding the switch ports. Later in the 1970s, we created the OSI model. So we broke up the TCP/IP from 4. We made it into 7 layers. It's really pretty much the same thing. We just have more layers to deal with. So why have a layered model such as this? Please write these down. It will assist in protocol design. In other words, if you are creating a router, all you have to worry about the protocols at the network layer. You don't have to worry about all the protocols at the transport or the data link. So it makes it a lot easier to design devices at the network layer or the NIC layer without having to know what everybody else is doing. Okay, so please write these points down. All right, you have to remember what the 7 layers at least. So take a picture of this. And the easiest way to remember it, I use the mnemonic. All people seem to need data processing. And remember, the application layer is on the top and the physical layer on the bottom. And when you're typing your, let's say, email, you start at the application layer. You're using Microsoft Outlook. Then you pass it to the presentation layer. Well, presentation layer may stamp some codes on the data that you gave it, your email, on how the fonts are going to be or if there's any encryption. Then you pass it on to the session layer. The session layer takes the data from the presentation and then it stamps a couple of labels on it to indicate when the session is open, when the session is closed. Then the session layer passes that data on to the transport layer. The transport layer will break up the data into little pieces called segments. And on each segment, it will place sequence number to identify which segment is first and which one second, and so on, and the port numbers. You see that the data is called, the PDUs, we call them protocol data unit. At each level, they're called the different names. And we are encapsulating the data. This is all happening inside your computer. Then from the transport layer, either TCP or UDP got it, we'll pass that data to the network layer, where IP protocol grabs that data and puts labels on it, such as the IP addresses. And there's a whole bunch of other labels. And once you put the labels on those segments that you received from the transport layer, then we call that a packet. So a packet is, inside the packet is a segment, and the labels on the packet is the IP addresses. Then that packet is given to your NIC, your network interface card, where it takes the packet and encapsulates that into a frame. And you see the word data link, you're going to link the data to the media. Media is the cable or the airwaves where the data actually gets transmitted. So the physical layer is where actual data is going to travel, the media. Anything that you see and touch in the network is physical, is at the physical layer. The standard, what type of cable you're going to use. Is it fiber? Is it coax? Is it a copper wire? What are the standards on which pins are going to transmit and receive, and so on. That's all part of the physical layer. And here's pretty much it's the same thing as the TCP/IP model, but the OSI model breaks the TCP/IP into 7 layers instead of 4. Okay, we pretty much talked about the data encapsulation. I just finished explaining to you how data gets encapsulated. So when the data is received, it gets broken down into segments, smaller pieces, and you may have to share. This guy and this young lady wants to pass data to the server, so you may have to share a cable. Data needs to be shared on the cable. This is called a trunk, right? So you break up the data. That's called segmentation. Multiplexing, meaning we take turns in using the trunk to send the data to the server. Okay, so write down this bullet point. Segmentation is the process of dividing a stream of data into smaller units for transmission over mark. Why do you need to divide it? Because there's a limit to how much data you can send. Okay, benefits of breaking down. That speeds things up a little bit, because the smaller you are, the faster you go, and the less likely you'll get corrupted. And more efficient, of course. Sequencing. When you break it up, you got to identify which is the first packet, the second segment, the third and fourth, so that when the destination receives them, he'll be able to reassemble the data. That's what each one of those segments must have a number on it, called a sequence number. Because number 1 and number 2 and number 3 and number 4, they may get to the destination at different orders. I only look at the numbers to actually put the whole package back together. So that's why you need sequencing numbers. And I said, as I said to you earlier, as we are encapsulating the data at each level, it gets different names. So up to the session layer, from the application presentation and the session layer, we call it data. Once we pass the data to the transport layer, and the transport layer breaks up that data into what we call segments. So the PDU at the transport layer now is called segments, because it has the sequence numbers and the well-known port numbers, right? And then when the segments are passed to the internet layer will add labels to each of these segments, and now they are called packets. So a packet is a segment with IP addresses on it. And then that packet is given to your NIC, and your NIC will encapsulate that packet into a frame. So the PDU at the data link layer is a frame. What's inside the frame? A packet. Okay, and then the frame is then placed on the media at the physical layer, placed in bits. So what is the PDU, the protocol data unit at the physical layer? It's bits. So we got data up to layer 5, segment at layer 4, packet at layer 3, frame at layer 2, and bits at layer 1. There you go. Take a picture of this. You will get this on a CCNA test or even on a CyberOps test, asking you what type of PDU at each layer as you encapsulate the data before it goes out in bits on the internet. All right, so we discussed all that. These are the labels as they are attached, right? You got the data, the segment. When you add more labels, it becomes a packet. When you add more labels at the NIC, it becomes an Ethernet frame. And then when you place that data on the wire, you place it in ones and zeros, and these are bits. And you receive them. De-encapsulating them is when you capture the data, the bits, you take the whole frame up, then you remove the frame, pull the packet out, remove the packet, pull the segment out, move the segment and pull the data all the way to the application. That's decapsulating it. Decapsulating is when you're grabbing the data and open up the boxes, right? All right. So, and that ends the chapter. So please take a snap picture of the last. This is why we have done this. Take a screenshot of this. A screenshot of all the summaries. Okay? All right. So again, it's 42 minutes. Please try. I hope you will take your time studying this. All the notes that I asked you to, please submit them as proof in a Microsoft Word. And I will see you on the next chapter, chapter 6.